Okay, so basically in this video we will try to see how do you raise matrix to the power n, how do you exponentiate a matrix, how do you take logarithm of a matrix and such things. Now before all of these, it's essential to know like how do we write a matrix in the form of PDP inverse. Yeah, whereas P is another matrix and D is a diagonal matrix. P can be any matrix, but D is a diagonal matrix that is in the form of A0, 0B. So if you don't know like how do we write a matrix in this form, I will link a video over here where I have basically written a matrix 2, 2, 2, 2 in this form. And basically the form we got in the previous video was this was 1 minus 1 1 1 0 0 0 4 and 1 minus 1 1 1 inverse. Basically you can see that this is diagonal element and there are pp inverses as well. And if we write a matrix in this form, there are a lot of benefits, such as in this form, it's easier to raise to an exponent or exponentiation or logarithms. And in this video, like we will see the proofs of these statements, yeah, and how do we do them. Okay, so now let's begin. So let's say we wrote a matrix in this form, PDP inverse. Okay. Now if you want to find a square, what you can do is we can multiply this twice. Yeah, PDP inverse times PDP inverse. Now we know that matrix multiplication has associativity. That's why we can write this as PD times P inverse P times DP inverse. Okay. Now P inverse P is just the identity matrix I. So we have PD times I times dp inverse. Now I times any matrix is just that matrix. So we now have P and the other matrix itself. And now again use associativity. We have D times D times P inverse. So you see that this is just P D square times P inverse. Okay. Now similarly, if you try to find a cube, you will just get P D cube P inverse. And similarly for a to the power n, P d to the power n times P inverse. Now, what's the benefit? Even though we don't have to find a to the power n, now we have to find d to the power n. But the thing over here is, finding d to the power n is actually easy because our diagonal matrix is in the form of A0, 0B. Yeah. Now if you want to find, let's say, d square, this is easier. I will show you how. Basically, if you try to multiply, what you get is, so this is a square plus 0. Yeah, a square plus 0. And then this thing is a times 0 plus 0 times b, 0. 0 times a plus b times 0, 0. 0 times 0 plus b times b, b square. So you see, again, if you try to find d cube by multiplying a square 0 0 b square and a0 0b, what you get is just a cube 0 0 b cube and so on. Like if you want to find d to the power n, you will just get a to the power n 0 0 b to the power n. So with such simplicity we can easily raise d to the power any exponent. So that's why now we can say that it's easier to find d to the power n. So that's why for any matrix, let's say if d is in the form of a0 0b, yeah, and we have a matrix A which is written in this form. So let's say we have to find a to the power 100, then just bp and then a to the power 100 0 0 b to the power 100 and then p inverse. Okay, so finally the first problem is solved. How to raise to a nth power. Yeah, now let's see how to raise a matrix to the power of a. Okay, let's say if you want to find e to the power a, we will use the series expansion for e, which is, now we can write this as a to the power 0 by 0 factorial plus a to the power 1 by 1 factorial plus a square by 2 factorial plus a cube by 3 factorial and so on. Yeah. Now to find a to the power 0, we already know that this is p d to the power 0 times p inverse by 0 factorial. If you ask me how, I already show you how to raise a matrix to the nth power over here. Yeah. And then we have p d to the power 1 p inverse by 1 factorial. And again p d square p inverse by 2 factorial. Yeah, and you can like basically use the constant to multiply any of the matrix, doesn't matter. And then p d cube p inverse by 3 factorial. Yeah, now you can take p common. Yeah, basically because matrix also has distributive property, you can take p common. Yeah, and it should be from the front side. So we have d to the power 0 by 0 factorial times p inverse, and then d to the power 1 p inverse by 1 factorial plus d square p inverse by 2 factorial plus d cube by 3 factorial p inverse. Now again you can take p inverse common from the back side, yeah, because distributive property holds. That's why you have p, and then t to the power 0 by 0 factorial plus t to the power 1 by 1 factorial plus t to the power 2 by 2 factorial, and this goes on, and then p inverse. Now you see this is just p in e to the power d by, and then p inverse. Okay, so now let's say if we have d as a0 0 b. Okay, so in that case what we can do with this statement, basically we from here what we can write is, so basically let me give a curly bracket over here. So we have p and some expressions and then p inverse. Okay, so now over here d to the power 0 by 0 factorial. Yeah, so that will basically be since we know that d to the power n is just a to the power n b 0 0 b to the power n, we can use that and we will get okay, so a to the power 0 0 0 a to the power 0 by 1 factorial 0 factorial. Yeah, we can take the constant insides, so that's why if we take constant inside, we will get a to the power 0 by 0 factorial 0 0 a to the power 0 by 0 factorial. Okay, now for the second term again we do similar thing, a to the power 1 by 1 factorial 0 0 a to the power 1 by 1 factorial. Now for the third term again a to the power 2 by 2 factorial. Yeah, you can understand. Yeah, oh, this is not a, this is b, sorry for that, b, and then 0 0 b square by 2 factorial. Now this continues, and yeah, and then we have p inverse finally over here. Okay, so now if we add these matrices, what do we get? P, and then over here we have a to the power 0 by 0 factorial plus a to the power 1 by 1 factorial plus a to the power 2 by 2 factorial and so on. Yeah, and now this is 0, this is 0, this is again b to the power 0 by 0 factorial plus b to the power 1 by 1 factorial, and this goes on. And finally we also have p inverse over here. Yeah, so now this is just p, and then this is e to the power a, yeah, again infinite sum, e to the power a 0 0 e to the power b, and then p inverse. Okay, so now we finally proved the second statement as well, I guess. Yeah, second was e to the power a is just p times e to the power d p inverse, which is p times e to the power a 0 0 e to the power b. Yeah, and then p inverse. Okay, second is also proved, and third also has a similar proof. Yeah, so basically we can use the following thing. We know that ln of x is basically x minus 1 minus x minus 1 whole square by 2 factorial. Basically, I have used the definition of ln of 1 plus x actually. Yeah, this is x minus x square by 2 factorial plus x cubed by 3 factorial. So I'm using the definition. So we have plus x minus 1 cubed by 3 factorial and so on. Yeah, now again we can write this as x minus 1 minus x square minus 2x plus 1 by 2 factorial plus x cube minus 3x square plus 3x minus 1 by 3 factorial and so on. Okay, so this is the infinite series expansion for ln of x. Now what we have seen in the previous proof is that, so basically whatever the infinite series is, the same infinite series will continue to the terms that are inside the matrix as well. So to the terms of diagonal matrix, the same infinite series is will come. So basically what this means is, if we can write any like function as an infinite series, so that will just go if apply to each individual term. So basically what will happen is, because if we have a p d p inverse, now if we take ln of a, what happens is we will have p and then to each term of d. So basically we will have a, yeah, and then okay, so basically if we write this as a to the power 0, so then minus 1 will be, because here is also 1 a to the power 0 in the home a to the power 0, 1 minus a square minus 2a plus 1 by 2 factorial. Yeah, sorry. Yeah, so same thing will carry on to the individual terms as well. Okay, over here b minus, we will have b to the power 0 actually, minus b square minus 2b plus 1 by 2 factorial, sorry, by 2 factorial and so on. Yeah, so that's why we will again in our p inverse over here, and that's why we will again have p times ln of a 0 0 ln of b times p inverse, and this will also be same as p times ln of the diagonal matrix times p inverse. Yeah, so we proved the last one as well. So these are some pretty fascinating ideas, and these are also helpful. If you want to know how this is helpful, like there's a three blue one brown video over here that will give you an idea on why this is useful. So, and also I hope that you checked my playlist of matrix algebra, where I have already shown how do we diagonalize a matrix in this form PDP inverse. And yeah, I do hope you have now the proof of why this holds true. Yeah, and I think this should have pretty much fascinated you. Yeah, thanks for watching. Look forward to seeing you in the upcoming videos too.